Okay, so for the second lesson in the finance notebook, lesson 6, um, let's look at two financial instruments, bonds and loans. And so again, start importing our libraries. And so here's an example that we can take a look at and see how to approach it using Python. Consider a newly issued 10-year, $1,000 par value, 10% coupon annual paying bond. The coupon payments will be $100 at the end of each year. The $1,000 par value will be paid at the end of the year 10. What are the previous present values for discount factors? 12%, 10%, and 8%. Okay, so let's create an array of discount rates first. And then using NumPy's present value formula, we can get all the different present values as long as we pass in, a future value of $1,000, the number of periods to be 10, and a $100 payment now. In the previous lesson, we mainly didn't deal with the payment piece, and so this will give us the present value according to each discount rate. So you could see yourself, in a real example, you could have hundreds of bonds with different discount rates and start looking at what if scenarios. And so these are different present values of each discount rate given keeping everything the same. So this shows us that the discount rate increases the value or price of a bond, as the price decreases. So calculating the value of the same bond with semi-annual payments. Okay, so to deal with semi-annual payments, you're just going to half the rate and double the number of periods because they used to be annual. So now we're paying twice a year, and that's a bigger frequency. And so, it still keeps it the same because we left everything. So, yep, it's still very similar. And so, yeah, so here's zero coupon bonds have no coupons, so we're setting it payment equals 0. Now, in one of the initial lessons, we kind of created a class on its own, but this is just using a NumPy previous class. So here's setting the payment, and you can see how it affects the present values. So NumPy also has a discount rate formula that function because you can, if you have all the other values of the all the other attributes, you can always find discount rate given present value and future value. And so yeah, so here we are getting those rates back. So we fed in the present values as an array with the payment, so with the same same terms, and yet we get back our original discount rates. So that means that this is internally consistent. And so in reality, the discount rate changes according to market rates at different times. So how are we gonna, so this is the yield to maturity based on the sum of future cash flows from the bonds, coupons and principal, is equal to the current price of the bonds. It is the internal rate of return if the investor holds the bond until maturity. And here's some further, and we can see, okay, it's actually closer to yield to maturity is actually closer to 4.93%. Okay, and then we have another present value, 15%. Not sure why I have this here. Okay, so for the next, so that was quickly doing some very introductory bond valuation. So for loans, um, what is the monthly payment needed to pay off a $450,000 loan in 30 years at an annual interest rate of 4%? So we can figure out the payment needed for this using NumPy's payment formula, right? So compute payment against loan principal plus interest. And so that is that's quite useful. You could see this being a mortgage, and here we are figuring out the principal for. Okay, so we've done just the no. This is the entire payment. So if we want to figure out the principal portion of that payment, pass in everything, we're using principal payment function from NumPy. Pass in the same arguments to the parameters, and you get $648 for the first period. And then what is the interest portion of that same payment? $1,500. But no, we can create with NumPy. If you pass, an array of periods, it will calculate them all for you in one shot. So what we can do is we can start creating an amortization table. So right now, I'm just saying create a data frame. This is kind of going back to our data analysis lesson. Create a data frame, but just create one column, period being using the arrange function, which is similar to Python's range function. Just going to create 1, 2, 3, 4, 5, up to 360 periods. So amortization head will just show you the first 5 rows of a data frame. Okay, so that's it. We still have an index that starts at 0, but we can ignore that for now. Looking at period. And now we're going to pass in that column into the principal payment. Now, we've been doing absolute values when I'm showing this, so just note that this does come back negative. So we're going to also continue with the element-wise absolute value version. So this is just the scalar Python of absolute value, and this one is going to run absolute value on the return of all these elements here. So when we went principal, we just went through the interest portion. So we're just going to run that, and we're going to do some calculations that we're kind of familiar with, column-wise calculations. So we're going to add up principal and interest. Now we could also have just run the numpy.payment function, and it should have been the same. And so what we're also going to do here was come back to our accumulative sum of the principal, and then we're going to subtract it from the original amount of the loan, and that will set like a rolling balance. And so we're going to, this is formatting to 2 decimal places for pandas, and we're going to take a look at this. Here we built out an entire amortization schedule that pays off the balance at the 0 from from a starting balance, $450,000. Now this is paid up. This is paid the first. This is already paid the first payment, and yeah, so it's 1 to 360, and there you go. So this is the final lesson. There is an assignment notebook that goes through some of this uh, to look at for the finance section. All right, thank you.